Welcome to Brain Vision.
For this problem, on the topic of photons, we want to know the minimum potential difference that's required between a filament and target of an X-ray tube if we are to produce X-rays with a given wavelength, and that is a wavelength of 0.15 nanometers. We then want to know what the shortest wavelength that could be possibly produced in an X-ray tube is if we are given the operating voltage. So we'll use the equation Hc over lambda is equal to E times V, where lambda is the wavelength of the X-ray and V here is the accelerating voltage. So in part A, to find the accelerating V, if we are given the wavelength, this is simply by rearranging the equation above, Hc over E times lambda. So that's Planck's constant H, which is 6.63 times 10 to the minus 34 joule seconds times the speed of the X-ray, which is 3 times 10 to the power 8 meters per second. All of this divided by the charge on the electron E 1.6 times 10 to the minus 19 coulombs multiplied by the given wavelength of 0.15 nanometers, which is times 10 to the minus 9 meters. So calculating, we get the accelerating voltage to be 8.29 times 10 to the 3 volts, or 8.29 kilovolts. For the next part of the problem, we are given the accelerating voltage and want to find the minimum wavelength of the X-rays that will be produced. So we can use the same equation and rearrange for lambda to get lambda is equal to H times C over E times V. So again, if we substitute our values, that's 6.63 times 10 to the minus 34 joule seconds multiplied by 3 times 10 to the power 8 meters per second divided by E, which is 1.6 times 10 to the minus 19 coulombs times the voltage in this case is 30 kilovolts, or 30 times 10 to the power 3 volts, which gives us the minimum wavelength of 4.14 times 10 to the minus 11 meters, which is 0.0414 nanometers.